Okay, so now we're going to consider an interesting and important example of rotational dynamics, and that's the example of a massive pulley. So up until now, we've considered our pulleys to be ideal in the sense that they are virtually massless, which means they have virtually no moment of inertia, which means they present virtually zero resistance to changes in their angular velocity. So by exerting, negligible counterclockwise torque, we can get that wheel spinning faster and faster and faster in the counterclockwise direction. Okay, and so when we drew pulleys before, we always put the tension to be the same on both sides of the pulley. That changes now if we consider a massive pulley. If we have a massive pulley, imagine some kind of a big cast iron kind of pulley. Okay, there's a large moment of inertia, so it requires a considerable amount of net twisting force to cause, any appreciable amount of angular acceleration. Okay, so to illustrate this, we'll consider the simplest possible example that contains all of the essential physics. All right, so we're going to consider a pulley, which is actually a uniform disc. We have a massive pulley here. And this massive pulley has a bearing at the center here that it can rotate around. And we support that bearing, this axle here, we support that with a rod attached to the ceiling. Okay, so now this pulley is just hanging on its axle here, frictionless axle, and it can rotate clockwise and counterclockwise with zero friction. And then what we do is we take a length of rope and we take that rope and we hang it over the top, wind it around the top of the pulley, and have it come back down on the other side. And then we attach two blocks to either end of that rope. So we attach a block of mass big M to the left end of the rope and a block of mass little m to the right end of the rope. And we're going to assume that big M is bigger than little m. Okay, so that if we release this system from rest, what's going to happen is big M is going to accelerate down, at the same time little m will accelerate up, like this. Okay, now we're only assuming big M is bigger than little m for the purposes of drawing the directions of the accelerations. If this is reversed, then our accelerations, either linear acceleration or angular acceleration, will come out to be negative numbers. Okay. So, okay, great. So we've got that. And then we say, we say that this pulley here is not frictionless. Okay, because if this pulley were frictionless, then when we release, then big M would accelerate down and little m would accelerate up, and the rope would just slip over the top of that pulley. So what we do is we assume there's static friction between the rope and the top half of the pulley, so that when big M is accelerating down, little m is accelerating up, there's a force of static friction, which is exerting a counterclockwise torque on that pulley, getting it to spin faster and faster. Okay, great. And then what we say is, so assuming that big M is bigger than little m, then when we release the system, then big M is going to be accelerating downwards, and it will also have a velocity at any instant of time downwards. So the velocity and the acceleration of big M at any instant of time will be downwards. And of course, the velocity and acceleration of little m will be exactly the same as big M, but in the upwards direction. Okay, so at any instant of time, big M and little m have exactly the same magnitude of velocity and acceleration. Okay, now, while this is happening, while big M and little m are doing this, while this wheel, big M is falling down faster and faster and faster, and little m is falling up faster and faster and faster. And so this pulley is spinning faster and faster and faster. So it's undergoing some angular acceleration, alpha. And at any instant of time, it has an angular velocity, omega. Okay, and so what we're going to do is we're going to take angular velocities of the pulley and angular acceleration of the pulley, and any torques that are applied to the pulley, any twisting forces applied to the pulley, we're going to take these as positive if they are counterclockwise. So we need to assign a sign convention. Okay? And what else? And of course, remember that when we're talking about angular accelerations and angular velocities, say counterclockwise, what we really mean is these things, the alpha and the omega, are actually vectors. And so, so alpha, angular acceleration, is a vector which comes out of the board, and omega is angular velocity is a vector which comes out of the board. So remember, for angular velocities and angular accelerations, they're vectors, and you put your thumb in the direction of the vector, and then your fingers curl in the direction of that angular velocity or angular acceleration. Okay. What else? Okay, so now we're going to give some properties here to the pulley. So we will say that the pulley has a radius r, and it has a mass mu. So we need some kind of an M-type letter, and so we've already used big M and little m, so we'll use the Greek letter mu to indicate the mass of that pulley. And we will suppose that that pulley is a disk, so a uniform disk. And so the moment of inertia for rotation about the center of mass of a uniform disk is ICM equals 1/2 the mass of the disk times the square of the radius of the disk. Okay, so we've got that. And I should also mention something about the tensions in these ropes. So normally when like in the past, when we were dealing with ideal pulleys with zero moment of inertia, then whatever tension we assigned to the left-hand rope, it immediately was the same tension in the right-hand rope. That's no longer the case. So first of all, let's assign a tension capital T to the left end of that rope. And that tension T, just incidentally, you know that that tension T has to be less than the weight of the block mg, because the net force is a weight pulling down and a tension pulling up. So the tension upwards has to be less than the force of gravity downwards, so there's a net downward force causing that acceleration of big M downwards. Okay? And then we'll assign a tension little t to the rope on the right-hand side, which will not be the same as big T, and it will be less than big T. But also, this tension T, if little m is accelerating upwards, there must be a net force acting on little m upwards. And so that one of those force, we have an upwards force of little t, the tension in the rope. We also have a downward force of gravity, little mg. So it must be that little t is bigger than the weight of the block with mass little m, so there's a net upwards force causing that acceleration, that linear acceleration A upwards. Okay, so we know that big T is less than big mg and little t is bigger than little mg. Okay, but also, and this is the crucial thing, is big T has to be bigger than little t, so that there is a net counterclockwise torque causing the angular acceleration of the wheel alpha. Okay, so when it's like net force is mass times acceleration, net torque is moment of inertia times angular acceleration. So we have the net torque, so that's the sum of the torques that are exerted about the center of mass of that wheel, of that pulley. That net torque is equal to, let's work this out. So So we talked a little bit about, there being a force of static friction all along here and so on, but effectively it's the same thing as this, at any instant of time, the same thing as this left rope under tension capital T exerting a force on that point of the pulley. That's the point of application of the force. So a force downwards of magnitude T applied at that point on the pulley. And so there's going to be a torque in the counterclockwise direction, whose magnitude, or say positive, whose magnitude will be the moment arm or the lever arm distance times the perpendicular force T. So the torque that that big T, the left rope, exerts on that pulley is positive, capital T, positive R times capital T. Let's write it as R times capital T. Okay, so positive R times capital T. And then similarly, the rope on the right-hand side is under a tension little t, and it is effectively exerting a force on the pulley of magnitude little t downwards at exactly that point. And so there's a lever arm R there, or a moment arm R, and so the torque, that little t, is exerting is negative. It is in the clockwise direction, and it is of magnitude the moment arm distance r, times the perpendicular force little t. Okay, so that's the net torque that's acting on that, and that net torque causes angular acceleration. So that's equal to the moment of inertia of this pulley times its angular acceleration. And if big M is bigger than little m, then this is going to be positive. Okay, and so the crucial thing here is that when the pulleys that we're dealing with are ideal or massless or have zero moment of inertia, then ICM here will be zero, and it doesn't matter what alpha is, the net torque is just zero. That's why we assign equal tension to both left and right hand side previously. Okay, but now when we consider a moment of inertia that's not zero, this is not zero, and of course we want the angular acceleration to be not zero, it's spinning faster and faster and faster, then this is no longer zero, in fact it's positive. Okay, and so what we see is that the tension big T must be bigger than the tension little t. So we can no longer assign equal tensions to both sides of the pulley in sort of a realistic situation like we're dealing with now. So we see that the tension in the left rope, big T, must be bigger than the tension a little t in the right in the right hand rope. Okay, and so you can think of it as big T here is exerting a counterclockwise torque, which helps alpha. Helps the counterclockwise angular acceleration, whereas the rope under tension little t, a lesser tension, is exerting a clockwise torque which hinders counterclockwise acceleration. Okay, and so because big T is bigger than little t, then there's a net twisting force in the counterclockwise direction, which is causing the angular acceleration alpha of that wheel. Okay. What else? Okay, so now we're going to do dynamics. So we have actually three objects in motion here whose dynamics we need to consider. We have masses big M and little m, which are in linear motion, and so we say, well, the net force, sum of all the forces, is equal to the mass times the linear acceleration. But now we have a third object which is undergoing angular acceleration. So we need to add up the net torque on that object in rotation and set that equal to the moment of inertia times the angular acceleration. So we have linear acceleration and angular acceleration in our problem. And so we have three objects in motion undergoing some dynamics, and so we need to draw three free body diagrams. Okay, so the free body diagram for big M is really easy. So we just have a mass, big M, and the forces acting on it are gravity. There's a field force pulling down of magnitude, say, big mg. And there's a rope attached to the top. There's a contact force pulling upwards with a magnitude T, capital T. And we know that because the acceleration is downwards, the downwards force of gravity is larger than the upwards force from the tension in the rope, and that's causing an acceleration, a linear acceleration, A, downwards. Okay, and the equation, a Newton's second law applied to this, says, well, the net force in the downward direction is mg minus the tension capital T minus okay, and so that net downward force is the inertial mass of the object times its acceleration downwards. Okay, so we will call this equation number 1. Okay, and then we do a free body diagram for the block of mass little m. So what we've got is a block of mass little m. Okay, and the forces acting on it, there's a field force gravity pulling down, which is little mg, and little mg, the downward force on little m, is smaller than the downward force on big M. Okay, but there's also an upward force, little t, coming from the rope, and that little t is smaller than big T, so it's shorter than big T, but it also has to be longer than mg. So maybe it looks like that. Okay, and so that net upward force is causing a linear acceleration A upwards. And so we apply Newton's second law to this, and we say, well, the net upward force is T minus mg, and that should equal the inertial mass of that block times its upwards acceleration. Okay, so that's our second equation. That's equation number 2. And now we have a third object that is undergoing accelerations, in this case angular accelerations. Okay, so the object is in rotational motion. Okay, so here is the free body diagram of the pulley. So we draw the pulley, and as we said before, the idea is, what are the contact forces here that are acting? Well, the ropes are exerting forces. So the rope on the left at any instant of time is effectively exerting a force of magnitude capital T downwards. So the force is of magnitude capital T downwards that's applied exactly at that point on the wheel. So that's capital T, and it's applied a perpendicular distance r, a moment arm distance r away from the axis of rotation. Okay, and then the rope on the right-hand side is effectively exerting a force on the pulley exactly at that point of magnitude little t downwards. Okay, so there's a force of magnitude little t downwards applied at exactly that point on the wheel, which is located a perpendicular distance r away from the axis of rotation. Okay, so we have that. Now, there are other forces, of course. So there is the gravitational force. So gravity is pulling down everywhere on this massive wheel, and it's effectively the same as a single force of gravity pulling down at the center of the wheel of magnitude mass of wheel mu times g. So the downward pull of gravity. There's also the downward pull of these two ropes of magnitude big T plus little t. But the thing is not accelerating downwards, and that's because there is an upward force that this rod is exerting on the axle upwards. It's like a normal force upwards. So the normal force that the rod is exerting on the axle is equal in magnitude to the weight mu g downwards plus big T plus little t. But we don't care about that. Okay, so the net forces in the vertical direction cancel out. There's no linear acceleration of that pulley up or down. But we don't care about that. What we care about is the net twisting force, or the net torque, causing the angular acceleration alpha. Okay, so we've already talked about that. So, so this rope on the left-hand side is exerting a counterclockwise torque. So that's of magnitude r times t, and the rope on the right-hand side is exerting a clockwise torque of magnitude r times t. So the net torque is r times capital T minus r times little t. That's the net torque in the counterclockwise direction. And we set that, like net force is mass times acceleration, net torque is moment of inertia I of the wheel times its angular acceleration alpha. Okay, and so that's equation number 3. Great. So now you look at this and you say, well, wait a minute. We've actually got 4 variables that we don't know. We don't know the we don't know the linear acceleration A, we don't know the angular acceleration alpha, and we don't know the two tensions, capital T and little t. That's 4 unknowns, and we only have 3 equations. Okay, so this is really important. There is something that you do know. Whenever you have pulleys wrapped, ropes wrapped around pulleys, and there's objects with linear acceleration, then that linear acceleration is not independent of the angular acceleration if there's no slipping of the rope. Okay, and so you can see that. Let's just put it down here. We're sort of out of room here. So we have this pulley over here, and we have that pulley is undergoing some angular acceleration alpha in the counterclockwise direction, spinning faster and faster and faster. And so if we look at a point on the rim of the wheel here, a radial distance r away from the center of the wheel, we know that this point is undergoing tangential acceleration at this instant of time. Acceleration meters per second squared, a tangential. Okay, which is equal to the radial distance r times the angular acceleration. So this is radians per second squared times meters is meters per second squared, is the tangential acceleration of this point on the wheel, upwards. However, this point on the wheel is attached by a rope to the mass little m, which is undergoing a linear acceleration a. And obviously, the instantaneous acceleration of that point of the wheel upwards is equal to the instantaneous acceleration of little m upwards like that. And so a tangential is equal to a tangential, the tangential acceleration of that point on the wheel is equal to the linear acceleration of little m. So this is an important relationship. So whenever you have, a situation where you have angular accelerations and linear accelerations, there are typically relationships between those things that you need to sort of understand. And so we'll call this important equation number 4. Now we have 4 equations and 4 unknowns, and we just solve those. Oh, right, I also wanted to point out that since we have 3 objects here that are exerting forces on each other, and they're exerting forces on each other through the tension in these ropes. Okay, so the tension. So there's Newton's third law action-reaction pairs of forces. Okay, so this rope under tension capital T is exerting an upward force on big M. It's also exerting a downward force on the rim of the wheel at exactly that point there. Okay, so this this one and this one are Newton's third law action-reaction pairs amongst your free body diagrams. And similarly, the rope under tension little t is at the same time exerting an upward force on little m, that's this guy, and a downward force at exactly that point on the wheel. Okay, so that's that. So these two are also Newton's third law action-reaction pairs of forces. So remember that whenever you have multiple objects in motion that are exerting forces on each other, draw the diagrams independently and then double check at the end that you have all the right Newton's action-reaction third law pairs of forces. Okay? So, great. So that's it. So now we just solve this equation. So what we're trying to solve for is the angular acceleration of that wheel. And so here's the angular acceleration of that wheel. So let's start with the third equation. So the third equation says ICM alpha is equal to R times capital T. And so equation number 1 tells us what capital T is. Bringing it over to the other side, because positive capital T is big M times G minus A. Okay? And then subtract big R times little t. And we solve equation number 2 for little t, and that's little m times G plus A. Little m G plus A. Okay? And then what we're trying to do is so we're trying to solve for alpha. So on this side we should collect terms that are proportional to G and collect terms that are proportional to A. And so that what you get is there's an R, capital R, times big M minus little m times G, and then there's a negative R times big M plus little m times A. Is that right? Yeah, okay. So then you say, well, great. So I've solved these 3 equations here. I've used all 3 equations. And so I've got an alpha on the left-hand side, and I've got an A on the right-hand side. But here's where equation number 4 comes in, super important. We're solving for alpha, so let's eliminate A in this equation in favor of alpha. So A is equal to R times alpha. Now we have an alpha there, and then a term that's just proportional to G there. And so this is one equation and one unknown, so I'll let you solve that. So what you end up with is, because I'm running out of room here, what you end up with is alpha, the angular acceleration of that pulley in the counterclockwise direction, is R times big M minus little m times G divided by ICM plus the sum of the masses times R squared. Okay, so that's our answer for alpha. Okay, so this is our answer for the angular acceleration of that pulley. The important question now, after sort of solving this physics problem, is to see whether it makes any sense. Okay, so you'll notice that the denominator is positive, always positive. But in the numerator, we have a big M minus little m, okay, a difference, and so they could be plus or minus, could be positive or negative. So we assumed that big M was bigger than little m. in which case the numerator would be positive, and we have positive angular acceleration. So counterclockwise, this wheel is spinning faster and faster counterclockwise. But if we can just flip this around and say, well, let's suppose that big M is less than little m, in which case the numerator here is negative, and the angular acceleration is negative or clockwise. Okay, when this guy's more massive than this guy, the acceleration goes like that. Okay, and it's clockwise or negative angular acceleration. Okay, so that makes sense. But actually, there's a really interesting way to think about this. So you'll notice that in solving this problem, we never, the answer does not depend in any way on the lengths of these two ropes. Okay? So what we can do in this problem is, at any instant of time, we can instantaneously imagine that those two ropes are of zero length. And effectively, what we've got is a system that looks like this. We've got a wheel that has, or a pulley, that has a moment of inertia, ICM, for rotation about its center of mass. And if we instantaneously make those two ropes of zero length, then effectively at that instant of time, we've got an object of mass, big M, glued to the pulley at this point. That's big M. Okay, a radial distance r from the axis of rotation. And we've got, if we make this rope instantaneously zero length, then we've effectively got a mass little m glued to the wheel at that point. Okay, so it's little m. Almost out. I have another one here. Okay. Mass little m glued to the right-hand edge of the wheel there, a radial distance r away from the axis of rotation. And if this was our situation, at this instant of time, we look at this and we say, what is the total moment of inertia of this system of the pulley with two masses, big M and little m, glued to it? Well, the moment of inertia would be this. It would be ICM for the wheel itself, plus the moment of inertia for two elemental rigid bodies. In other words, a mass, big M, a distance, big R away from the axis of rotation. That's a moment of inertia, big M R squared. Similarly, little m attached this distance r away contributes a moment of inertia, little m R squared, to the moment of inertia of our new object here. Okay, so in the denominator here, what we have is the effective moment of inertia for this system over here, where we've instantaneously set the lengths of the ropes to zero. Okay, and then we say, well, we know that angular acceleration is net torque divided by inertia. This is the effective inertia. What's the net torque? Well, the net torque is just, at this instant of time, we've got gravity. Gravity is pulling down everywhere, but it's symmetric. The only asymmetry in the problem is we've got a mass, big M, sitting here, and gravity is pulling down with a force mg, and hence exerting a torque, a counterclockwise torque of magnitude r times big mg. Well, there's the r times big mg. Okay, and at this same instant of time, we've got gravity pulling down on mass little m. So gravity is effectively grabbing the wheel at that point and pulling down. And so that's exerting a clockwise torque of magnitude moment arm, lever arm r, times perpendicular force mg. So there's the r mg, and it's negative because it's clockwise. Okay, and so this is really the net torque, so the effective torque. So the effective net torque. So, so what's nice is to take a problem like this, and you've solved it all, and then stare at the answer a little bit and see whether you can make sense of it. So in fact, you could have guessed this answer right to begin with. You could have just said, oh, well, I can just take those ropes to be of zero length at any instant of time, construct this object. I know the moment of inertia of that object is just ICM plus big MR squared plus little mr squared, and the torque at that instant of time is this numerator. And you could have just written down this answer without doing all of these calculations. You just sort of eliminate the ropes right to begin with. We did this sort of mathematically by looking at these equations and eliminating the torques, the tensions, big T and little t, in finding this answer for alpha. Now we could go on and we could calculate big T and little t and see that, yes, indeed, big T is bigger than little mg and little t is less than big mg, and yes, the torque, big T is bigger than, so the tension big T is bigger than little t, and so on and so forth. Okay, but so this is a really nice example of rotational dynamics applied to a very practical situation of massive pulleys. Okay, and so if you understand all of the, if you understand this problem deeply, you will have, a good understanding of, rotational dynamics.